In the last video, we derived how we can get the Gibbs free energy equation, which allows us to relate the entropy and enthalpy values. So enthalpy change and entropy. So you can see that this value can change as we adjust the temperature. We learned last time that in the second law of thermodynamics that for a spontaneous process, delta S of the universe is positive, is always increasing. So if we take, remember delta G is a negative T times the delta S of the universe. So if we have a positive increase, or we have an increase in the entropy of the universe, and that means my delta G value will be negative since I'm multiplying it by a negative temperature. So then my delta G for a spontaneous process will be negative. So that's what we're going to be going off of. And so both the sign and the entropy of enthalpy and entropy, as well as how large the temperature is going to matter in regards to whether a reaction will be spontaneous or not. So here's this problem. We have this reaction. Notice that we have two gas molecules going to two gas molecules. If we calculate the entropy from the tabulated values and also the enthalpy, we get these. So notice that it's an endothermic process since delta H is positive and it is increasing in disorder. So we're going to solve for delta G will help us to know if the reaction will be spontaneous, and it is at 298 Kelvin. So I'm going to do 180.7 kilojoules minus the temperature, which is 298 Kelvin. And notice the entropy is in joules per Kelvin, so we want to get it into the same units. And Gibbs energy is generally measured in kilojoules, so I'm going to take my 24.7 joules per Kelvin and I'm going to convert it into kilojoules. So I have 1,000 joules in 1 kilojoule. So that means my entropy is 0.0247 kilojoules per Kelvin. So I'll plug that in here. So 0.0247 kilojoules per Kelvin. Notice my Kelvin cancels out and I get my value. So once I calculate that, I get 173.3 kilojoules. So this is non-spontaneous. It's not spontaneous. At this temperature, we can actually calculate at what temperature it will turn to be spontaneous, because that value where we go from a negative to a positive or vice versa is 0. So what I can do to find the temperature at which something becomes spontaneous is set delta G equal to 0 and solve for temperature. So I'm going to do that here. So I'm going to find out what temperature I should be spontaneous. So I'm going to do delta G equals delta H minus T delta S. I'm going to set that equal to 0. Plug in 180.7 kilojoules minus my temperature, which I'm trying to solve for, times 0.0247 kilojoules per Kelvin. So I'm going to solve for T, so I'm going to add over this part. So I get 180.7 kilojoules equals temperature times 0.0247 kilojoules per Kelvin, divide by my entropy value. Notice my kilojoules cancel out. My denominator of a denominator becomes my numerator. So the temperature at which we go from a positive to a negative value is 7,300 Kelvin, and I'm rounding. So very high temperature for this reaction to become spontaneous. So like we said before, if delta G is negative, the forward reaction is spontaneous. If delta G is positive, then it's non-spontaneous in that direction. But if we reverse the direction of the reaction, that will be spontaneous because we would flip the sign. And when delta G is 0, the system is at equilibrium. So we can see here that this is the reverse reaction, being spontaneous, the forward reaction, making it so we always are getting to this minimum value of delta G being 0. So we can also look up Gibbs energy of different compounds in the textbook, just like in our table 19.2 and also Appendix C. So just like with enthalpy and entropy, we do products minus reactants. So you'll be able to practice that in your homework, as well as working on the trends. So if we think about what's going to make our Gibbs energy be negative or spontaneous. So here's our reaction. Delta G equals delta H minus 2 delta S. So to be spontaneous, delta G needs to be negative. So if we have a delta H negative, that's going to help us to be spontaneous. And then I'm going to subtract a delta S part. So if delta S is positive, then this whole thing will help us to get more negative. So when delta H is negative, so we have exothermic increasing disorder, we will always have a spontaneous process. So the opposite is going to be true too. If I have an endothermic reaction that decreases disorder, then I'm always going to have a positive delta G, so I'm always going to be non-spontaneous at all temperatures. But this is where it gets tricky. So if I have an exothermic process that decreases disorder, so my enthalpy is helping me to be spontaneous, but my entropy is not. So we want to figure out a way to minimize this entropy term. So what we could do is at low temperatures, the delta S factor gets really small and my exothermic process will help me to be spontaneous. So at low temperatures we'll be spontaneous, and at high temperatures the entropy component will get bigger and it will now be non-spontaneous. If I have an endothermic process that increases disorder, now my enthalpy is not helping me to be spontaneous, but my entropy is. So now if I have my temperature be really high, this component gets extra big and it can outweigh the enthalpy. So we saw that on the last practice problem. It had to be a really high temperature, over 7,000 Kelvin, before it hit to be spontaneous. So this will be spontaneous at high temperatures. So we're going to practice. This first one is just using the Appendix C values to figure out what the Gibbs energy of this reaction is. So delta G for the reaction is going to be products minus reactants. So I'm going to do 4 times the Gibbs of PCl, 3, minus, so that's my products. My reactants are going to be a P4 times 1 and 6 chlorine. So when I look up those values in the book, I get 4 times phosphorus chloride is negative 269.6 kilojoules per mole, minus phosphorus P4 gas is 24.4 kilojoules. So, and there's only one of them, so 1 times 24.4 kilojoules plus 6 chlorine, and chlorine is 0, so we don't have to add that. So when we do this math, we get a value of negative 1102.8 kilojoules. If we have the reverse reaction where we have 4 PCl3 gas goes to phosphorus gas plus 6 chlorine gas, then our delta G for this reaction is positive 1102.8 kilojoules per mole, and that would be non-spontaneous where our original reaction is spontaneous. Now in this process, this Haber process is the way that chemists have found to make ammonia, and for that reaction, this is an exothermic reaction, so it has a negative enthalpy, and it decreases in entropy, which makes sense because we have 4 gas molecules here and only 2 here, so it went down, there's the value. So we're going to predict what's going to happen to delta G as we increase the temperature. So I have delta G equals delta H minus T delta S. Since we have an exothermic process minus a decrease in entropy. So the one thing that's going to bring it to make it be spontaneous is enthalpy. Enthalpy is negative, which is going to help our Gibbs be negative, or the entropy is helping it to be more positive. So we want the temperature to be low if we want this reaction to be spontaneous. So we could predict that as temperature increases, our delta G will become more positive due to the entropy effects. So we're going to calculate now the delta G at 25 Celsius and 500 Celsius. So first thing we got to realize is we don't want Celsius, we want Kelvin. So we're going to plug in to this equation here. So at 25 Celsius, if we add 273, then we get 298 Kelvin. So our delta G is going to be negative 92.38 kilojoules minus our temperature, 298 Kelvin, times by our entropy change, so it'll be a negative. And we want to make this in kilojoules, so we need to divide by 1,000, which will make it 0.1983 kilojoules per Kelvin. So when we calculate that whole thing, we get our delta G at this temperature is negative 33.3 kilojoules. Now at 500 degrees Celsius, that we're going to add 273 to get 773 Kelvin. So our delta G is going to be the same numbers, negative 92.38 kilojoules, minus our temperature of 773 Kelvin, times by our entropy, same value. So in your calculator, you can basically go back and just replace the temperature. And when we do that, we get a value of 61 kilojoules. So you'll see we went from a negative value, spontaneous, to a high temperature being non-spontaneous. And we could actually calculate at what temperature in between 25 and 500 Celsius it changes from being spontaneous to non-spontaneous by just solving G equal to 0 and finding the temperature. So in this putting our concepts together problem, we have a trinitroglycerin, which is known as nitroglycerin, used as an explosive. It has been used both to make dynamite as well as to help relieve chest pain. So fun fact, so at 1 atmosphere and 25 Celsius, our enthalpy of decomposition to form nitrogen gas, carbon dioxide gas, and liquid water, and oxygen gas, very big decomposition, is this. So that's delta H of that reaction. So first we're going to write the balance equation for the decomposition. So we'll have nitroglycerin, C3H5N3O9. I believe it is a solid that decomposes into nitrogen gas, carbon dioxide gas, water, and O2. So a lot of products. So we will just start off first by balancing. This is just going to be my process. If you want to balance on your own, I think that's a good thing to practice. So I have 3 carbons, so I'm going to put a 3 here. And actually, first thing I want to do is notice I have 3 nitrogens here and 2 here. So immediately I know I need to multiply everything by 2 in order to be able to get the same, an even number of nitrogens. So if I multiply that by 2, then now I have 6 nitrogens on each side. So I'm going to have 3 here. Now that I have that, I have 10 hydrogens. So I'm going to have 5 there. I have 6 carbons. So I'm going to put 6 out front. And now I need to deal with my oxygen, so that's fun. So I have 18 oxygens on this side, and then I have 12 here, 5 here, and 2 here. So that's an odd number on my product side, so I'm going to need to multiply everything again, fun, by 2. So let me erase. So I'm going to multiply that by 2 and put a 4. Now I'm going to multiply, that will become 6, 12, and 10. So 6, 12, 10. So everything should still be balanced, and I'm going to redo. So now I have 36 oxygens, 24, 10. I'm going to erase. 24, 10. And we'll figure out how many we need here. 24, 10. So now I have 34, 36. So I just need 1 here. And there we go. Now we're balanced. So that's fun. We'll erase this. Now we're going to calculate the standard heat of formation of this process. So the heat of formation of this molecule. So we know that the reaction, so delta H reaction, is negative 1541.4 kilojoules. Now what I want to do is, I know that delta H reaction equals the products, delta H of the products, minus delta H of the reactants. So I know the reaction, delta H, is negative 1541.4 kilojoules. So my products are, I have 6 times nitrogen plus 12 times CO2 plus 10 times water, liquid, plus 1 oxygen. And I'm going to subtract my reactant and my delta, so the delta H of my reactant, that is the nitroglycerin, so C3H5N3O9. Okay, so we can look up these values in the book. So get negative 1541.4 kilojoules equals, now nitrogen and oxygen are in their elemental state, so they'll become 0. So when we look up in Appendix C, we have 12 carbon dioxide, and carbon dioxide in the gas form has an enthalpy of negative 393.5 kilojoules, plus 10 water, liquid water, and that gives us, liquid water has negative 285.8 kilojoules. So those are our products, and we're going to subtract our reactant. Now that's what we're trying to solve for, and there's one of them, so we'll just call it X. So we can move this whole thing over, so by subtracting, and when we end up solving after you rearrange some things, we get the delta H of formation of our nitroglycerin, C3H5N3O9, equals negative 353.6 kilojoules. Now it says a standard dose of this is 60 milligrams, or 0.6 milligrams, assuming it is completely oxidized, so reacted. What number of calories is released? So we'll want to convert that into we'll use our enthalpy of formation, or enthalpy of reaction, to figure that out. So I'm going to take 0.6 milligrams, and I'm going to do, there are 1,000 milligrams in a gram. Now we can look up the molar mass of the trinitroglycerin, and we can find, when you add it up, it's 227 grams per mole of nitroglycerin. I'll put Ng. And I know in my reaction, for every 1 mole of nitroglycerin, it releases 1541.4 kilojoules. And now I will convert that into calories. So for so 1 calorie, we'll do kilocalorie, the big one, is 4.184 joules. Actually, that should be kilojoules. So when we do that, we get, actually, I'm going to go to regular calories. So then I have 1,000 little calories in 1 kilocalorie. And so what I get is 0.97 little calories in this amount of nitroglycerin, so very small. So one common form of nitroglycerin melts at 3 Celsius. So from the information in the formula, would you expect it to be molecular or ionic compound, and explain? So we think of ionic compounds as like salt, table salt, chalk, those kinds of things. Molecular being like sugar, water, stuff like that. And if you remember, molecular compounds are only made up of nonmetals. And ionic compounds are a metal plus a nonmetal. So if we look at the structure, being C3H5N3O9, those are all nonmetals, leading us to believe it's a molecular compound. Also, melting at 3 Celsius is a pretty low temperature. Ionic compounds like salts, those are solid at room temperature. So the fact that it melts at 3 Celsius lets me know that it's a nonmetal, or it's a molecular compound made up of nonmetals.